Good morning, ladies and gentlemen. I've been tempted all along to give the lecture once in a different accent. Austrian, for example, or maybe Switzerland, or Saxonian, would be Anglo-Saxonian. But maybe I should continue in my homegrown Franconian accent. At least you got used to that. All right. This is the last lecture with new material. Last time we talked about the final section of the book underlying the lecture, namely the derivation of Chandrasekhar's dynamical friction formula. The idea was that you have a large mass moving through a collection of small masses. The effect is that the large mass will collect small masses behind itself by the focusing effect that its own gravitational action has on the small masses. So it will create a wake, Kielwasser, a wake of small masses behind itself, which will slow itself down. And we saw that this effect leads to a mass segregation because dynamical friction depends on the large mass squared. And so the effect is much stronger for large masses than for small masses. And we see this mass segregation, for example, looking at galaxies in galaxy clusters where large masses collect in the center and small masses. Large mass galaxies collect in the center and small mass galaxies stay further out. We also saw that in the limit of small velocities of the large mass, the dynamical friction becomes or acquires Stokes type, right? The friction acceleration due to the friction will be proportional to the velocity itself, while at high velocities the friction effect will be much smaller. Right? So you have an effect that starts mildly and then becomes stronger and stronger and leads to large masses ending up in the center of the mass distribution of small masses. I emphasized, at least I tried to emphasize, the assumptions that go into the derivation of Chandrasekhar's dynamical friction formula. And these assumptions and the limitations that come with them are one reason why you find in extended literature about modifying Chandrasekhar's dynamical friction formula. So far, so good. Do we have questions about this? Have you experienced dynamical friction? Probably not. All right, so today we are going to do something different. I was thinking that, damn it, I was thinking that since we have already covered all the material that I wanted to cover, we might do something funny at the end. And for that, I will return to Liouville's equation and add collision terms on the right-hand side. Right, so far, in any circumstance where we encountered Liouville's equation, in plasma physics, for example, or now in stellar dynamics, we either neglected collision terms or we argued that by taking velocity moments over them, they're going to disappear, like in hydrodynamics. But sooner or later, you can't avoid collision terms, and then let's see what happens. So the idea today is, first of all, to look at the Liouville equation augmented by collision terms, and then to introduce approximations for these collision terms which have turned out to be extremely useful. And then I will conclude with an astrophysical application, which is really, really stunning. And on the way, we will close the loop of the lecture, the loop of subjects that we ran through in the course of the lecture. Namely, we will return to radiation processes in the form of Compton scattering. Nice, huh? Isn't that elegant? All right. Good. This will fall asleep. Should be no problem. Okay. Is that all? No. No, it isn't. Okay. So let's start. Our first goal is the derivation of the so-called Fokker-Planck equation. And of course, there are different, let's say, manifestations of it, but let's go through that. All right. The starting point is that we had the Liouville equation, and remember where that comes from. Right? This is just the evolution equation of phase-space density under symplectic dynamics. Right? The little fact that there is a minus sign in the Hamiltonian equations, an asymmetric minus sign, leads to this equation here. All right, the minus sign is the signature of a symplectic form in phase space, and the consequence is Liouville's equation. So we can change Liouville's equation by introducing additional types of force, and we call them collision terms. And these will be, they will have to be non-Hamiltonian, right? Because if it were a Hamiltonian, you wouldn't escape the consequence of Liouville's equation. And this is typically mediated by direct collisions between particles. They're functional of the phase-space distribution itself. That's the point. And now we'll see what we can insert here for the collision terms. I will deal with a transition probability psi, whatever that is, right? From some point in phase space to some other point in phase space that is dx away. So x bundles the phase space coordinates, q and p, could be something else, right? You could think of something much more abstract. You could think of defining your distribution function not on phase space, but on some abstract state space. The quantum mechanical state space, for example, right? Hilbert space. And then, of course, you would have transition probabilities from one state in Hilbert space to another. So this is just an example, and the example we need most often, right? Transitions in phase space. But much more generally, you could think of transitions in state space. All right, so X is this, and I will avoid writing a vector arrow here just to illustrate the principle. And later we'll have to think about the complications that arise because we have a vector here. Okay, so that's the transition probability. And that's the phase space coordinate. All right, with this thing here, and together with the phase space distribution itself, I'm now going to write down an expression for loss terms, for gain terms and for loss terms. And I mean with that, terms that either enhance or reduce the phase space distribution f at a certain phase space point x. Right, so I focus on f of x and t, and I want to know how many particles will be added to that point in phase space, or how many particles will disappear from it. So there will be a gain, and of course all the particles that you want to gain at a certain position x in phase space must come from elsewhere. And so this is going to be an integral over all changes all changes delta x in phase space coordinates, in the phase space position. Now we'll have a transition probability from x minus delta x by delta x. Okay, and the logic of, let me write delta here to be clear about this. in the logic of the definition of this transition probability here, transition probability from phase space point x by delta x. We now need to start from x minus delta x so that we arrive at x, and we are going to multiply this by the phase space distribution at the starting point. Right? So this is just the number of particles that you gain per unit time at phase space position x. Okay, there will also be a loss term. And this, of course, will be caused by all particles that are scattered away from the point that we are looking at. All right, you might have different terms, right? Particles could decay, for example. They could be created, whatever, right? But here we are looking at the change in phase space density by collisions with other particles, mediated by this transition probability here. All right, and of course, df dt will be the difference between gain and loss. And so this leads to an integral over all possible changes in the phase space coordinate x. And now the gain is this, so this is psi of x minus delta x times f of x minus delta x. All right, and we are going to subtract psi of x and delta x times f of x. All right. Sometimes this is already called the Fokker-Planck equation. To my taste, that's a bit early, because the essential trick of the Fokker-Planck approximation is, of course, now to make a Taylor approximation, right? And say, okay, if delta x is small, then of course the form of this difference between gain and loss suggests a Taylor approximation. Aha. If delta x is small, what does this mean? Then by all collisions that you have, the phase space position will change not very much. It will change by a small amount only. This is the key point of Fokker-Planck, right? The assumption that you have diffusion in phase space. It's a diffusion process in phase space then, because particles move in phase space only by a small amount. Of course, that's again an approximation, right? They could jump by a large amount. But that's not the point. Here we are going to assume that particles do not move much. You have a diffusion process in phase space. Okay. If you don't know else, then you have to stop here, right? Then you have to quantify the transition probability and see what it really looks like, and then you can evaluate the whole expression. All right, but let's now assume small delta x and make a Taylor approximation in delta x. So this will approximately be psi of x delta x times f of x. See, I'm using as the starting point for my Taylor approximation that position in phase space, and now I have a negative change to it, namely minus dx of psi of x and delta x f of x times delta x. Okay, if I stopped at this point, you would have no effect. It turns out later. So we need to go to second order. Second order will be a positive contribution, so you'll have plus a half. Now dx squared, same expression. And now delta x squared. Let me skip over the fact that, of course, x is a vector. Right? X is a six-dimensional vector, and so the derivative with respect to x is also a six-dimensional vector. So what I'm doing here, dx squared, is to create from this scalar expression here a 6 by 6 dimensional matrix, which I'm going to multiply by these two 6-dimensional vectors here. So that's a quadratic form. Yeah, We'll need to take care of this later, but for the moment we don't need that. Okay, now if I insert this Taylor expansion in phase space into this expression, of course, then the term psi f at the position x is going to cancel out. And we arrive at df dt is this huge integral over all possible changes in phase space, delta x. And now minus dx. And now I'm going to write psi f, right? Because now the argument is always, because of our Taylor expansion, it's always reduced to x comma delta x. Okay. So you arrive at this point. This very often is also called the Fokker-Planck approximation, or the Fokker-Planck equation. Now we are coming closer to the actual matter, right? Because now we have already assumed that we have a small change of the phase space coordinate only. So this is already a diffusion process in phase space. Okay. Now what? Now we are going to integrate over delta x, but have derivatives with respect to dx. Right, so I can write the whole thing as this expression here. Times that. Okay. But look, we are integrating. Okay, fine. Let me emphasize this a bit. Okay, this way. All right. But now, if you think of the arguments of the psi and f functions, psi does depend on x and delta x, so we have to keep it under the integral, but f does not. Right? F just depends on f. So I can pull this out and write this in the following form. This is dx, some quantity d1 times f. Derivative applies to both. Plus dx squared, some quantity d2 times f. Right, because f can be pulled out from the integral. Okay, what are d1 and d2? d1 by definition is the integral over delta x of psi times delta x. And d2 by definition is a half integral d delta x psi delta x squared. These are the diffusion coefficients in phase space. Okay? A first order and a second order diffusion coefficient. Okay, now this is starting to get interesting, isn't it? So we could, for example, if we know the physical process that is responsible for the collisions between the particles, we could evaluate these diffusion coefficients once and for all, and then evaluate this expression here for the specific situation, that is, for the specific phase-space distribution that we have in mind. Of course, under the assumption of diffusion, but okay. diffusion in phase space. Now, yeah, let's do this here. I can write this a little bit differently, but before, let me say more specifically what I mean with these expressions. So you see here, since delta x is a vector and psi is a scalar, this whole expression here is a vector. And this expression, you should imagine this square as a tensorial square, right? So this expression is a matrix or a tensor. That's a diffusion tensor here. So what do these derivatives mean? Well, this is a shorthand notation for dxi d1f I. Right? So d1f has components I, and you apply the I components to that. So this is actually divergence here. Very interesting. This expression here means it's this one, right? So this is also a divergence. It's the divergence of the vector that you get by taking the divergence of this tensor. All right? Look at the box as it is moving up. Now I'm going to write df dt is obviously the negative divergence of a current density. Okay? No, a current density. The current density is given by what? It's d1f. Remember, d1 is a vector, right? So, all right, d1f. Now, minus dx d2f. And again, right, the dx applied to the tensor d2f is actually a divergence. And these are all divergences in phase space for now. Right? It's going to simplify as we move on. Okay, so our Liouville equation with collision terms, also called the Vlasov equation, can be brought in the Fokker-Planck approximation into a manifest conservation form. So you have a diffusion current in phase space here, and we can write the diffusion current in this way by means of the diffusion coefficients d1 and d2. And remember, d1 is a vector and d2 is a tensor. Okay. All right. Now, if you had an equilibrium distribution f bar, let's say, then of course you would expect the current to vanish. And this establishes a relation between d1 and d2. So ultimately we will have to deal with only one of them. Lovely. And since we will have to apply a divergence to the tensor d2, let's eliminate d1, that's easier. All right, so the equilibrium current density, that must be zero, otherwise it wouldn't be equilibrium. And this requires that d1 of f bar minus the phase space divergence of d2 times f bar, that this thing must vanish, and of course this establishes a relation between d1 and d2. So this means that d1 is 1 over f bar times the phase-space divergence of d2 times f bar. Aha. Let's go a little bit further now and resolve this divergence. So if I apply the divergence to the complete term here, I will have an f bar times the divergence of d2. The f bar cancels, so this will just be the phase-space divergence of d2. And then, if I apply the divergence here to f bar only, I get plus d2 times the phase-space gradient of f bar divided by f bar. And that's the phase-space gradient of log of f bar. Aha. So it looks like this. Yeah.
I have a question. Why are we neglecting that like there could come divergence from the f bar term? Because normally wouldn't we
it's the gradient here. Right? This is a tensor, and now you multiply the tensor with a vector nabla x f bar. All right. Now, of course, I can insert this d1 into our original expression for the phase-space current density. Let me start over here. So now, with this expression for d1, I get d1 times f. Okay, so this divergence plus d2 nabla x ln f bar. Aha. This beautiful thing is d1 only, so I need to multiply this with f, and now I need to subtract the divergence of this term here, and again, this is f times the same logic as before, right? F times nabla x, f times the divergence of d2, and minus d2 phase-space gradient of f. See how nice this is. This one fights with this one, and they both lose. This one is multiplied with f here. So let's give this one an f2. And then we have the phase-space gradient of ln f also. And then the whole expression, no, that was not good. Okay. And then the whole expression looks like what? This is f minus f times diffusion coefficient or diffusion tensor d2 nabla x applied to ln f minus ln f bar. Okay, isn't that nice? That shows that the whole diffusion current is driven, of course, by a difference, in parentheses, the logarithm of the phase-space densities in reality and in equilibrium. And of course, once you reach equilibrium, this becomes zero and the phase-space current cancels. But of course, this is how we constructed it. All right. We've made a lot of progress already. Let's now assume the following thing. So far, so this box here belongs to the box above. So far we have dealt with phase-space coordinates as a whole, Q and P. Now let's assume we have diffusion in momentum space only. What does this mean? This means that collisions are so frequent that particles don't get very far in configuration space, so that I can neglect changes in configuration space altogether. Right? In other words, I may have a spatial dependence of the phase space distribution. Fine. But if the mean free path of the particles is very short, in comparison to the length scale characterizing the phase space distribution itself, then I can neglect, while I'm studying the change in momentum space, that there may also be changes in configuration space. In other words, now I'm going to apply a scale separation again. I'm comparing two scales. One scale on which the interaction of the particle is going to happen, short, and one scale on which the configuration space distribution of the particle is going to change, long. Right? So changes in configuration space are going to be small against changes in momentum space. So let me further assume that. Let me just write scale separation. So the mean free path lambda is supposed to be very much smaller than a length scale L. To remind of the notation we used in hydrodynamics, a length scale L on which the particle distribution is going to change in configuration space. Then I can write df dt is partial df dt. Why is that? Well, it would go on like this. The equation would go on like this. Due to Hamiltonian physics, this will be the gradient of h, the Hamiltonian negative gradient of h, the Hamiltonian function. If this assumption applies, then this gradient can be, the gradient of the Hamiltonian can be neglected. Goes away. There's a configuration space gradient anyway. Okay? So by this scale separation, I can neglect everything in parentheses. And the left-hand side of our equation just returns to dTf. Okay, lovely. So what does this describe now? This is now, what will result will be an equation that is local in configuration space. Okay, and almost local in momentum space. It describes a spatially local diffusion process in momentum space. All right. Equals minus. Now, of course, the gradient with respect to the phase space coordinates will turn into a gradient with respect to momentum only. And this will now be, the J will now be a current density in momentum space. All right, so this will be F d2 nabla P. This is now a gradient only ln F minus ln F bar. All right. And at the same time, the diffusion coefficient d2, this is going to be a half. Now let me emphasize that this is now a vector p, because even that is going to change soon. So let me write d3 delta p may p. Okay, over what? Our transition probability. Now that will be a transition probability characterized by P and delta P instead of X and delta X. And then we will have the tensor product of delta P. Okay? That's an average. That's an average over the transition probability. So this is going to be 1/2 times that here. It's a dispersion tensor. Okay? All right. So now we are here. And we have again lost much of the complication that was in the original Fokker-Planck equation. So now it's a momentum space diffusion term, a momentum space diffusion equation, which, according to our scale separation, is local in configuration space. Okay, fine. So often you find this as Fokker-Planck equation. Now this is Fokker-Planck equation the third. Right? Fokker-Planck equation the second was this. Fokker-Planck equation the first was this. And you find the name for many different things. All right. Now I need more space on the board. So let me wipe a little bit. And then we are going to further specialize the situation. And of course arrive at Fokker-Planck equation the fourth. So now let's make the following further assumption. Let's suppose that the momentum change, delta P, may change the angle of the momentum P by an arbitrary degree, we don't care, but may change the absolute value of the momentum only by a small amount. That's a perfectly reasonable assumption if you scatter small things off large things, for example. Right? Then you will have almost no energy exchange between the two, therefore almost no change in the absolute value of the momentum. But things may fly somewhere, right? So suppose you have a stream of sand particles, right, that hit a huge, let's take table tennis balls, okay? Suppose you throw a table tennis ball at a medicine ball, a thing like that. The energy of these table tennis balls, if they hit the large ball, will not change, except for a very small amount. But their direction will be somewhere. They will fly somewhere in the room. That's the situation we have now in mind, right? Delta P will have an arbitrary angle, but maybe only a very small change, if at all, in absolute value. So then, what I should consider is not the phase-space distribution as a function of the vector P, but the number of particles contained in a shell of radius P. Radius P plus dP, right? So, what are we going to do? the assumption is now that the absolute value of delta P relative to the absolute value of P is going to be very small, but the angle will be arbitrary. So then I will need to look at the change of the number of particles in a shell in momentum space. Right? And the differential volume of that shell in momentum space is going to be, I know, 4 pi times p squared dp, but the 4 pi dp will appear everywhere now, so I'm going to drop it again. Okay, so we need to look at that. Now, I need to introduce the f times p square. Where are we? F times p square everywhere. All right. Let's see. So first of all, no. The gradient with respect to p will now turn into a dp only, right? Because now we have diffusion in the absolute value of the momentum only. Now, of what? Of jp. Now I need to write here fp square times d2 now times dp ln p square f minus ln p square f bar. Okay. So you see the following structure. First of all, if I now take a partial time derivative, this will not act on this p square here, right? Because the p square is just the surface, or just quantifies the surface of the volume shell with radius p. This is fixed in momentum space. So I can write on the right-hand side p square dtf, and now the f is a function of the absolute value p of the momentum and time only. All right, so then I get here plus dp. I can pull out the p square here and get f times d2. Now dp ln p square f minus ln p square f bar. All right, now you recognize the structure of a divergence in spherical polar coordinates. And if I now divide by p square, I get dtf is 1 over p square dp p square times something. Right? And this is the expression for the divergence in spherical polar coordinates. So what will remain here is the scalar current density Jp now. And it's scalar because it's the radial component of the current density only. What does it look like? Jp is what? F times d2 not sure all of what I'm doing is correct now. Let's see. So that's going to be f times ln p, no. ln p squared plus ln f minus ln p squared minus ln f bar, right? So the ln p squared drops out, and we get f times d2 dp ln f minus ln f bar. That should be correct. All right. So again, we get another variant of the Fokker-Planck equation. Which looks like this, which is now a purely scalar equation. You have the scalar expression for the divergence operator here, because it acts only on the radial component now, which is the p component of the current density, and the current density looks like that. All right. So what have we got? We have got df dt plus divergence in phase space of a phase space current density Jx equals 0. And to distinguish that from Jp and everything, I'm going to write Jx now. So Jx was minus f times d2. Now nabla x ln f minus ln f bar. That was Fokker-Planck the second, the diffusion in phase space. Or you take, or you restrict the diffusion to momentum space only, then you get this expression over there. So now you get partial f with respect to dt plus divergence of Jp equals 0, and the Jp was given by minus f times d2 this expression here, gradient ln f squared minus ln f bar. And now in the further approximation, that momentum changes only the absolute value of the momentum changes only very little, but the change in angle is free. You have, again, divergence of a scalar Jp. Let me write it this way here. And the scalar Jp is going, if I, in order to write it as a conservation equation, I should introduce a minus sign here, right? So that I get dtf plus divergence 0, and then the current density gets a minus sign as well. Then we have, very much like here, f times d2 dp ln f minus ln f bar. Okay, so now you have these three variants of the diffusion approximation in various stages. diffusion in phase space. Diffusion in phase space. You have diffusion in momentum space. And you have diffusion in absolute momentum. Okay, so far so good. Let's have a short break. Going to wipe the board. All right. Now, in order to move on, I'm going to jump to an application of the Fokker-Planck approximation for the absolute value in momentum space, this one here, which you can find in the book under the heading The Componates Equation. Componates was a Dutch physicist, and I have found no traces of him other than the Company's equation. What I'm going to derive now is not the complete Company's equation. You get the complete Company's equation if you take quantum physical processes in photon space into account, namely if you take into account that photons are bosons, and therefore transition probabilities are changed by boson statistics. So you have stimulated emission for bosonic particles, and you get additional terms in the Company's equation through that, which are not going to be covered by what I'm going to do now. But we are going to apply the Company's equation to a situation where this is completely pointless, right? Where you do not have any stimulated emission because the photon number density is just too low. All right, so the situation I have in mind is the following. Suppose you are a microwave background photon. You have been emitted approximately 14 billion years ago, but you haven't noticed, right? Because photons have no proper time. By the way, this makes me wonder whether photons have a boring life or not. Probably not. In any case, right, now you're traveling, and you keep traveling, and you keep traveling, and suddenly you reach a galaxy cluster. This happens to some of them. By the time you reach a galaxy cluster, you have traveled already very much, and the universe has grown old, and your energy has dropped by gravitational redshift or cosmological redshift. And since you have been emitted with approximately 3 electron volts, now that you reach the galaxy cluster, your energy has dropped to approximately 3 milli-electron volts. So you are a really, really tired photon. And then you get into this galaxy cluster, and the galaxy cluster has a temperature of approximately 10 to the 7 keV. Sorry, 10 to the 7 eV. Let's take 10 to the 6. It's more problem. Mega electron volt. What am I saying? No, sorry. We should have temperatures of the electrons in the galaxy cluster around a keV or 10 keV, and we are way below the pair production limit. But the energy of the electrons will be very, 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 very much higher than your own energy. Now, occasionally, by Compton scattering, you will be hit by an electron, and you will find yourself somewhere completely else in phase space. The electron won't have changed much. It won't have noticed much, right? Because it's very similar to that situation with the medicine ball and the table tennis balls that I talked about, right? The photon is very tired coming along, but the electrons are very energetic. And so in the rest frame of the photon, let's take the rest frame of the electron. It won't change much, right? It won't see much. Okay, so we have the very specific situation that, first of all, we have an energy hierarchy saying that h bar omega for the photons is going to be very much less than electron momentum squared divided by 2m. With m, I now mean the mass of an electron. So the kinetic energy of the electrons is very much higher than the energy of the photons, and this is very much smaller than mc squared, right? We are very, very well below the pair production limit. Okay, that's a clean scale separation in energy space. And under this assumption, you can return to our treatment of Compton scattering somewhere early in the lecture. Remember, it was last year and so on, where we found that the energy change of the photon divided by the energy of the photon is some formula. And if you apply these approximations here, you can write this approximate expression for the energy change of the photons. It's linearized in the photon energy, which is permissible because their photon energy is very low. And it assumes that the photon energy change is very, very small. The direction of the momentum, of the photon momentum, will change by or may change by a lot. Right? So these two vectors here, direction of the incoming photon, direction of the outgoing photon, they may be largely different. Right? But the energies will be very similar, just because the electrons are so much more energetic than the photons are. All right, so now this is the perfect situation for applying Fokker-Planck the fourth, right? Diffusion in the absolute momentum space. Now, what is diffusing? The photons are diffusing, right? So what we need to evaluate here is this expression for the current density and this expression here for the change in the phase space density of the photons. Okay, but what is D2? The diffusion coefficient, this is 1/2 times the average of delta P squared, right? Remember, we saw before that the diffusion tensor D2 is a dispersion tensor for the momentum. But now we have a one-dimensional dispersion tensor, right? Because we have reduced the system to effectively be one-dimensional in momentum space. So this will just be delta P squared. Okay. This is the change in photon moment, in absolute value of the photon momentum squared. What's the photon momentum? Well, this would be the photon energy divided by the speed of light. So the change in momentum is h bar over c times the change in frequency. Right, so I can directly go on here writing, okay, this is 1/2 h bar over c squared, delta omega squared. Okay, we know what delta omega is. So that's going to be omega squared. That was easy. What do we do with this thing here? We have no control over the relative angle between the incoming photon direction and the momentum direction of the electron it is hit by. So we have to introduce an arbitrary angle, let's call it alpha, and then I can write absolute value Pe squared of the electron momentum. Now I need to average, that's an average too, I need to average over cosine square of that angle. And I need to average over the square of this expression here. Right? And the square of this expression is the square of E, that's 1, plus the square of E prime, that's also 1, minus 2 times the cosine between the two. And I call this theta, and I get an overall factor of 2. Okay, because the square of this is 2 minus 2 times cosine theta. Okay, so you notice I have split up this average here into 3 different averages over the electron momentum squared, over the angle between the electron direction and the photon direction squared, and over the photon direction squared. So what I'm assuming here is that they are all statistically independent. Well, that's a safe bet, right? Okay. All of this is manageable. Let's start with this one. What is Pe squared? Well, if the electrons are thermal, then you know exactly what that is, right? Because this is 2 times the electron mass times the average kinetic energy of the electrons. But for a thermal electron gas, right, the average kinetic energy is 3/2 times kB times the electron temperature. I'm making use of the equipartition theorem here, right? Every degree of freedom on average gets kBt halves. That's why. Okay, very good. So this is 3 times m kBte. Okay, done. Now we can express the average electron momentum squared by the electron temperature. Lovely. Let's continue with that one. Well, what is this? It's the cosine square averaged over the complete solid angle. Right, so this will be 1 over the complete solid angle times the integral over cosine square alpha d phi d sine alpha d alpha. So what is this? 1 over 2, right? Because if I integrate over d phi, that cancels, and I get an integral, as usual, over mu squared d mu from -1 to 1. That's 2/3, and I get 1/3. Lovely. Look, even they agree. That all conspires to make our life easy. Okay, we need to average over 1 minus cosine theta, but here we need to take the Thomson scattering cross-section into account. Right? That's going to be a little bit more complicated, but not much. So we need to know what is 1 minus cosine theta averaged, and that's going to be 1 over the complete Thomson cross-section for normalizing. And now integral over d omega, the differential Thomson cross-section times 1 minus cosine theta. Okay. No surprise. So what is this? Integral d omega. Now, Re squared over 2, 1 plus mu squared. That's the differential Thomson cross-section. Remember, we did that in the beginning of the lecture. Times 1 minus mu. Okay, the phi integral just gives a 2 pi. So we end up with pi Re squared divided by sigma t. And now the integral from -1 to +1 d mu, 1 plus mu squared. Did I make a mistake? We had 1 plus mu squared times 1 minus mu. But look, we are integrating from -1 to +1, so every odd function will give you 0. But if you multiply this expression 1 plus mu squared with mu, you only get odd contributions. So I can write as well drop the mu. Okay, what is this? Well, the integral over 1 from -1 to 2 is 2. This one gives 2/3, as we just calculated. So that's 8/3. So we end up with 8 pi over 3 times the classical electron radius squared. Beautiful, eh? Beautiful. Okay. I made a mistake here. The mistake is that this is the diffusion coefficient caused by a single electron-photon encounter. You may have more than that. So we need to multiply how do we call that? D21, right? That's from a single encounter. Okay, now we need to multiply by the number of encounters. I don't know. Of course, we can only multiply by the number of encounters per unit time. But that's exactly what we need, right? So, number density of the electrons, Thomson cross-section, speed of light. I mean, the photons are going to be tired, but nobody keeps them from moving with the speed of light. Okay. It's funny, right? Even though they are tired, they always walk with the same speed. Good. Now, we need to collect terms. This is the number of collisions per unit time. We need to multiply this with a contribution to D2 from a single collision. D2 superscript 1. So that's Ne sigma T C. H bar omega divided by MC square. I'm collecting these terms, right? H bar omega divided by MC times C, the whole thing squared. Okay, now we move on. We have 3 times M kBTE divided by 3. So that's M kBT E, electron temperature, which is vastly different from the photon temperature. Right? The photons come along with about 3 kelvins. The electrons have on the order of 10 keV, 10 to the 7 kelvins. Okay, it's the electron temperature here, and that's important. Now we have already dealt with the average of cosine squared alpha. The average of 1 minus cosine alpha over the Thomson cross-section is 1, as we saw. So we are done. Aha. That's our diffusion coefficient. Isn't that interesting? So now we need to return, we are here now, right? We now have the photon diffusion coefficient. We should express the photon energy by the photon momentum, right? Because everything that we wrote down here deals with the momentum of the particles scattered. So we should substitute here that h bar omega divided by c is the photon momentum. So let's replace still h bar omega divided by c by the photon momentum. So then we have p squared. All right, then I would have mc left squared. One of these m's cancels. I would have c squared left here, c. One of them cancels. Okay. And then I have kBTE. And this can be written in a much nicer way. Or somewhat nicer way. We have Ne sigma T. Now I'm going to write times C again. It's the number of encounters per unit time. And then I get kBTE divided by mc squared. Right? That's the fraction of the thermal energy of the electrons divided by their rest energy. That's very easy to evaluate. And then we have p squared. All right. So far, so good. Now we make some convenient variable substitutions. I'm going to return now to Fokker-Planck the fourth. I'm going to insert all I have. So that's 1 over p squared dp. Now the scalar current density, so that gives me F. Wait, p squared. Now F times d2, I'm going to separate the p square from the d2, and then only constants are left, right? So therefore, I'm getting p to the fourth here, and then I need to drop the p square from the rest of from d2 in what follows, and then we have just dp ln f minus ln f bar. I have a minus sign here, because the current density was negative. So I bring this on the other side. And then I have the rest of d2, that's ne sigma t times c kbte divided by mc squared. And we're done. All right, now I'm going to introduce a variable x, which is a dimensionless version of the photon momentum. Namely, it's going to be h bar omega divided by kBt. This is now the photon temperature. Okay, we need to distinguish between these two because we have a thermal distribution of photons and we have a thermal distribution of electrons, but with vastly different temperatures. Okay, so this is Cp divided by kBt, so that's just a multiple of the photon momentum. Now we have -2, -3, +1, -1 powers of the momentum. In other words, if I want to substitute x for p, I can just as well write x instead of p, because all the prefactors are going to cancel. Right? They appear in exactly the same power. Okay, next I introduce a variable y by saying this is ne sigma t c kBte divided by mc squared dt. What does this mean? I'm replacing the time t by a variable that is appropriate for the scattering process. It's called the Compton y parameter. And as I said, right, it has the very intuitive meaning. This is the number of collisions per unit time. That's the average energy change per unit, average energy change per collision, and I multiply with time. Okay, so that's a dimensionless quantity that parameterizes the energy change that happens to the photons. And now I can rewrite the whole equation as the partial derivative of f with respect to the Compton y parameter. And this is now simply given by 1 over x squared dx x to the power of 4 f dx ln f minus ln f bar. Okay. That looks like a complicated thing. But now, what is f bar? that would be the equilibrium distribution between photons at energy 0.3 electron volts with electrons at energy 1 to 10 keV. If you bring them in equilibrium, the derivative with respect to the photon momentum of F bar would be negligibly small, right? Because the photons would just spread out in momentum space due to the very high momentum of the electrons. So F bar will be such that I can just neglect that. All right. This is getting nicer and nicer, right? Now we have df dy is 1 over x squared dx x to the 4th f dx ln f. Now what about f? F is the phase space distribution of the photons. I'm going to separate this into a spatial number density of the photons times a number density in momentum space. But I can factor out the number density in configuration space because the equation is homogeneous in F. Right, here we have an ln f, so any normalization of f would drop out anyway. And between those two factors f, I can cancel the spatial number density. So for f, I can simply insert the occupation number of the photons in phase space. And that you know very well, right? So for f, I can say this is 1 over e to the power of x minus 1. It's just the Bose-Einstein distribution. Okay. Right. Now, in order to work this whole thing out, let me rewrite this a little bit, and then we will shortly be done. So we have to do 1 over x squared dx, x to the power of 4 times f. Now dx ln f, this would be just dxf divided by f. Okay? So this is what I have to calculate. But f depends only on x. So I'm going to denote the derivative with respect to x with a prime. So we have 1 over x squared. Now I'm going to apply the dx to the x to the 4th. That gives me 4 times x cubed, and what is left is just an f prime from here. Or I pull the dx past the x to the 4th, then I get x to the 4th times f double prime. Okay, lovely. Now, I pull as much out as I can for the moment. So this would be x if I pull x cubed out. And what is left is 4 times f prime plus x times f double prime. Okay. Now, evaluating the f and f primes and f double primes is very easy. You know, because if this is f, then f prime is just minus f squared times e to the power of x, right? If I take the derivative of that with respect to x, I'm getting minus 1 over the same thing, so that's the minus f squared, and then I have to take the derivative of the denominator, and that's e to the power of x. Okay, so if I take another derivative, this is minus 2f prime e to the x, and now minus f squared e to the power of x. F prime I know, right? So this is minus 2 times f times minus f squared e to the power of x times e to the power of x minus f squared e to the power of x. So this is f squared e to the power of x times 2 e to the power of x minus 1. And f of x we know. All right. So let's return to that here. Four times f prime. That's minus 4 times f squared to the power of x, f squared to the power of x. Let's pull that out of the bracket right away. So then we have minus 4 plus x times 2e to the power of x minus 1 times f squared e to the power of x, right? So again, I need this, 4 times f prime. F prime is minus f squared to the power of, f squared times e to the power of x. I'm pulling f squared e to the power of x out, so minus 4 remains from here. Good. The double derivative also has a factor f squared e to the power of x. This we already have, and then we have x times this expression left. Okay. So this is x times e to the power of x, e to the power of x minus 1 squared. Something is wrong. Sorry. There was a factor of f missing. All right, now we are getting there. This remains correct, and now we have, what do we have? 2 times e to the power of x divided by e to the power of x minus 1 minus e to the power of x minus 1 divided by e to the power of x minus 1. So now we are here. Now if you pull this together, you see just e to the power of x plus 1 divided by e to the power of x minus 1 remains. And finally, we are getting this expression here. Okay? This does not depend on y. On the left-hand side, we have df dy. So we can immediately integrate and see, and this will now be the last thing, f equals, well, the whole thing here. This will be the phase-space density afterwards. You know what we started out from, right? Okay, now, what happens is really, really astonishing and beautiful. So you now know how we arrived there. Now, sorry. need to say it twice. Does that work now? Okay, look, what I'm showing you here is this the function of x that we just derived, right? This function here, excluding the y factor here. That's what I'm showing here. Multiplied with x cubed. Why? Because if you want to have an intensity, a photon intensity, you need to multiply the phase space distribution or the occupation number, first of all by the volume element in phase space, that's x squared dx. And then you need to multiply by the photon energy, which gives you another factor of x. So what I'm showing here is x cubed times this beautiful thing here. What do you see? You see it's negative. It's negative below some frequency here. There's a 0 point. So it's negative below that and it's positive above that. What does this mean? In comparison to a Planck spectrum, the Planck spectrum of the cosmic microwave background, the intensity at low frequencies is reduced, and at high frequencies it's enhanced. Why is this? Well, of course, because the energy of the the energy of the electrons is so much higher than the energy of the photons that you have inverse Compton scattering. Right? Every encounter with an electron will move the photon energy to a much higher value. So in comparison to a blackbody spectrum, photons will be missing at low frequencies. Interesting. Where's that 0 point? That 0 point is at 3.83. Look, x equals 3.83. Yes. No. What does this mean? Well, we know the photon temperature, 2.725 kelvins. So we can exactly calculate what frequency this is. That's 217.5 gigahertz. So in other words, our galaxy cluster will cast a shadow on the cosmic microwave background at frequencies below 217 gigahertz and will shine above that frequency. It will be a positive source above 217 gigahertz and will be a shadow below 217 gigahertz. There was a satellite observing the cosmic microwave background, the Planck satellite, that had 9 different frequency bands, and one was located exactly at 217 gigahertz just for that reason. Right? If you look at the microwave background at 217 gigahertz, you will not see any galaxy cluster. If you look at lower frequencies, and Planck had frequency bands between 33 and 857 gigahertz, if you look below 217 gigahertz, you will see a shadow. If you look above, you will see a source. If you look at the maximum here, if I remember correctly, that's 357, you will see them at their full brightness. In other words, galaxy clusters are very peculiar objects against the microwave sky. They are negative sources at low frequencies. They disappear at 217 gigahertz. They show up at higher frequencies. So by looking at difference maps, preferentially between 357, don't quote me on that, I think it's correct, preferentially at 357 against this one, don't know, and 217, you will find the maximum signal of a galaxy cluster against the microwave sky. So essentially you take a map of the microwave sky and you look at things that disappear at 217, are negative below and are positive above. And you find all galaxy clusters that there are. provided their signal is intense enough and so on, right? But this is the ideal way of finding a galaxy cluster. And then you see the Compton Y signal, the Compton Y parameter, is proportional to the electron number density times the electron temperature. Remember what X-ray emission was sensitive to, number density of electrons squared divided by the square root of the temperature. So by comparing the two, you get both of them, right? The number density in a galaxy cluster and the temperature. And if you knew the temperature from somebody else, right, for example, from X-ray spectroscopy, then you can infer with that particular effect the electron number density much more accurately. Beautiful, isn't it? This is called the Sunyaev-Seldovich effect, named after Rashid Andreevich, I think, Seldovich, and Yakov Borisovich. No. Rashid Andreevich Sunyaev, yes, and Yakov Borisovich Seldovich, who described this first in 1970. And there are two variants of the Sunyaev-Seldovich effect. This is called the thermal Sunyaev-Seldovich effect, of course, because it's due to the thermal motion of the electrons. You can also get a Sunyaev-Seldovich effect by the scattering of electrons moving in bulk. And the galaxy cluster is moving, for example, towards you or away from you and so on. And this leads to a Doppler effect in the scattered photons, which is called the kinetic Sunyaev-Seldovich effect. It's much smaller, much less important. So what we are looking at here is the thermal Sunyaev-Seldovich effect. By the way, Sunyaev for some years was my boss. A very interesting experience, I can tell you. All right, let's have a look at galaxy clusters. Look at this. This is a section from one of the Planck maps. Right? They did exactly what I described to you. Right? You get a high frequency map, you get a low frequency map, you get a map in between. And you ask, what disappears at 217? What shows up at 357? And what is negative at lower frequencies? In that way, you can create Compton Y maps. Right? Here you see one. And you see how the galaxy clusters beautifully stick out of this map. Because the signal is so peculiar, right? You're looking at something that disappears. You're looking at something that is negative. And you compare this to sources. Very beautiful. Okay, so here you see the galaxy clusters identified. And the color bar at the bottom shows the Compton Y parameter that is reconstructed from the strength or from the amplitude of the Sunyaev-Seldovich signal. Now you can look at individual galaxy clusters. Let me just show you two examples and then we are done. So on the left you see the Sunyaev-Seldovich signal from the Planck data of some cluster. I think it's the Shapley supercluster. And on the right-hand side, turned and twisted and whatnot, is the same galaxy cluster in the X-ray signal. And then you're looking at the same population of things, hot electrons, with both. Right? And in one case, they cast a shadow on the microwave background. In that case, you see, what do you see? Thermal Bremsstrahlung emission, just as we discussed it in the early parts of the lecture. Here is another example. Abel 3393 and Abel 3395. Of course, I showed you examples which are really peculiar. This is a pair of galaxy clusters which are in the process of merging. Right? They fall onto each other. How do we know that they haven't passed through each other already? Well, then you would see shocks. Right? Then you would see remaining shocks. You don't. So you know that you are looking at this accident just before it happens. It takes a while until it will finish, but okay. Again, you see the X-ray image to the right and the Sunyaev-Seldovich signal to the left. I think this is most beautiful, right? So what have we done? What I wanted to do today was to, first of all, show you what you can do if you need to take collisions into account. Of course, we have only scratched the surface. right? But we have scratched that surface in an important way, namely by deriving in total 4 variants of the Fokker-Planck equation. The essential idea of the Fokker-Planck approximation is that you can go further in the treatment of collisions if you assume that you have diffusion either in phase space or momentum space. And finally, we applied the whole situation, or we applied the whole approach to a diffusion in the absolute value of momentum. Right? And then we derived the Sunyaev-Seldovich signal here. As I told you, if you complete this approach by taking Bose-Einstein statistics, in particular by taking stimulated photon emission into account, gives you another source term, of course, right? And then you need to go through this calculation again. You arrive at a complete version of what is called the components equation. Here we do not have to take care of stimulated emission because the photon density is much too low, and so our approximation here is sufficient. So this is a special case of the components equation, but the components equation itself has many other applications wherever you have quantum scattering or inverse quantum scattering, as it may be. All right, done for today. Sorry for running over time. Last time I did in fact catch my train, which was not a problem at all, for reasons that you can think of. Everything else went smooth. I just arrived an hour later, but that was still enough. Okay, we're done. Next week, as I announced, I'm going to be here to summarize the lecture and to answer questions you may have. If you don't have any, well, fine. And then the week after that, Thursday, 10 to 12, there will be the written exam in the large lecture hall at Philosophers Walk 12, not here. If you come here, you made a mistake. All right. Thank you very much and see you next week, maybe.